All right, welcome to another deep dive today. We are going to be exploring some really, really unusual ideas, and I'm excited to get into it.
Yeah, this should be interesting.
You know, we received a document from a listener. Shout out to the listeners, by the way, for sending stuff in.
I always appreciate it.
Absolutely. And so this document is from Terrence DaShon Howard,
Oh, okay.
and it questions some really foundational math concepts.
Interesting. What kind of concepts are we talking about here?
Yeah, so like just the basis of multiplication,
Oh, wow. Okay.
the square root of 2. And, you know, our listener, you know who you are. You love these kind of aha moments, these really mind-bending, thought-provoking ideas.
Yeah, our listeners definitely like to get into the weeds a little bit, look under the hood.
Absolutely. So we're going to try to unpack these kind of unusual perspectives
Love it.
and just see what we can get out of it. You know, what kind of insights, if any, come from this this questioning of basic mathematics.
Yeah, absolutely. I think it's always valuable to kind of revisit those foundational things that we maybe take for granted and just to see if there's something else there, another perspective.
Absolutely. And, you know, I'm sure there will be some disagreements,
Oh, I'm positive.
maybe even some head scratching.
Almost definitely.
But that's kind of what makes this fun.
That's part of the journey.
That's part of the journey. So let's dive right in.
All right, let's do it.
So first off, Howard starts with multiplication. And he challenges this idea that 1 times 1 equals 1.
Okay, so like the most basic multiplication fact that we all learned in like elementary school.
I know, right?
All right, interesting. So what's his thinking there? Why does he think 1 times 1 does not equal 1?
Yeah, so he starts by looking at this inverse relationship between different mathematical operations.
Okay.
So he says, you know, if dividing 4 by 2 is the reverse of 2 times 2 equals 4, then by that same logic, dividing 2 by 1
Right.
should be the reverse of 1 times 1.
Okay, I follow that.
And so based on that, he kind of argues that just like addition, subtraction, and division,
Mm-hmm.
they all show this kind of consistent ratio, right?
Yeah.
So like, you know, if you add 2 and 2, you get 4.
Right.
You know, two things together make this new value that reflects, you know, both of them.
Yeah.
And it's the same with subtraction and division. But then when you come to 1 times 1 equals 1, he says, well, that doesn't quite fit.
So he's saying it breaks that pattern.
Yeah. And 2 times 2 equals 4, he's fine with. That seems to make sense to him.
Okay.
But 1 times 1 equaling 1, that's where things go awry.
So what's like the heart of his argument there? What doesn't he like about 1 times 1 equaling 1?
So he has this thing that he calls the unbalanced equation argument. And it basically states that if you have 1 times 1 equals 1, one of the initial ones, it just vanishes.
It disappears.
Poof.
Yeah.
Gone. It doesn't like contribute to the quantity on the other side of the equal sign.
Interesting.
And the way that, you know, the other operations do.
Yeah, it's like it's not really participating fully.
Exactly.
Okay.
And then he goes on to kind of define multiplication as repeated addition.
Okay.
And he calls doubling, he calls it the quote unquote first action of every interaction, end quote.
The first action of every interaction.
Every interaction, that's what he says.
Okay, so how does he use that to kind of bolster his argument against 1 times 1 equals 1?
Yeah, so if you think about multiplication as just repeated addition,
Mm-hmm.
then 2 times 2 makes sense. Right?
It's two added together, yeah.
Right.
Which equals 4.
Right. But then in his mind, 1 times 1 should be 1 plus 1.
Which would be 2.
Which would equal 2.
Okay, I see where he's going with this.
Right. So he sees 1 times 1 equaling 1
Mm-hmm.
as this kind of like non-event.
Like nothing really happens.
Yeah, there's no interaction. There's no change.
Okay.
And he uses this vivid image.
Oh, I love a good image.
He describes the number 1 in multiplication as acting like a phantom or a noble gas.
A phantom or a noble gas?
Okay. So it's like it's not really engaging with the other numbers. It doesn't change them.
Yeah, it's just kind of there, but not really participating.
It's just kind of floating around.
Okay.
But it's worth noting here that in standard math, the idea of a multiplicative identity that's 1 times anything is that thing.
Right.
That's a core concept. It's an axiom.
It's, yeah, like a foundational building block.
Yeah.
So he's really challenging something super fundamental here.
Yeah, absolutely.
Okay, so we're already kind of off the beaten path here.
Oh, yeah, just a little bit.
So where does he go from challenging this idea of 1 times 1 equals 1?
All right, so next we're going to move on to the square root of 2.
Okay. Another, concept that we probably all learned at some point in school.
Yeah.
Probably took for granted.
Probably took for granted.
Okay.
But he says this questioning of the square root of 2, it actually goes all the way back to his childhood.
Oh, wow. Okay. So this has been on his mind for a while.
Yeah.
All right. So what happened? What's the origin story here?
So he was fine with the idea that the square root of 4 is 2.
Mm-hmm.
But then he asked his teacher in 3rd grade, I think it was. He said, well, what's the square root of 2?
Right. A natural question.
It is a natural question. And the teacher apparently just kind of dismissed him and said, well, it's too complicated for you.
Too complicated. All right.
Which you can imagine for a curious young mind.
Yeah, I would not be satisfied with that answer.
It didn't sit well with him.
Yeah, it sounds like it kind of lit a fire under him.
It did, absolutely. And he was like, well, if 0 has a square root of 0 and 1 has a square root of 1,
Right.
why wouldn't 2, which is right there in between,
Yeah.
have a clean square root?
A nice, neat answer.
Right.
Yeah.
And so this really bothered him, and he says it motivated him for decades to really explore this question.
Wow, so this seemingly simple question from his childhood has really stuck with him.
Absolutely. And he sees this as a big problem, this idea that the square root of 2 is this never-ending decimal, like 1.42135.6.
Right, that irrational number that we all learned about.
Exactly. So what's wrong with that, in his mind?
Yeah, what's his beef with the irrational number there?
So he says that this irrational number is just an approximation.
Okay.
And he argues that it represents this flat, two-dimensional, non-existent, unreal thing.
Okay. A two-dimensional unreality.
And he says that's a problem because, we live in a three-dimensional curved universe.
Right. And in mainstream math, irrational numbers are considered to be very precise.
Right.
And they're kind of necessary to describe certain geometric relationships. Like if you think about the diagonal of a square, that's where the square root of 2 comes in. And, going back to ancient Greece, this is like a cornerstone of real number theory.
Okay, so his views on the square root of 2 really clash with a lot of standard mathematics.
Yeah, he's definitely taking a different approach here.
Absolutely. So then what does he propose as the actual square root of 2?
Yeah, what's his alternative? If he doesn't like the irrational number, what does he recommend?
So he says the quote unquote recommended value for the square root of 2 is 1.
1. Just the number 1.
The number 1.
Okay.
And his reasoning for this connects right back to what we were talking about with multiplication.
Right. So that idea of balance and ratios and inverse operations.
Exactly.
Okay.
So he explains that if you take the number 4 and divide it by 2, and then divide it by 2 again,
You get 1.
you get 1.
Okay.
And similarly, if you take 2 and divide it by 1 and divide it by 1 again, you get 1.
You get 1. So it's that same kind of consistency across the operations that he was talking about with multiplication.
Right. He's looking for that balance.
Gotcha.
And so just like he argued that 1 times 1 should equal 2.
Right. To be consistent with addition.
To maintain that consistency.
Right.
He's saying that the square root of 2 should be 1 to kind of maintain that inverse relationship with division.
Okay, so that's a pretty big departure from how we normally think about square roots.
Oh, absolutely, yeah. In the standard way of thinking, squaring 1 just gives you 1.
It gives you 1, not 2.
And taught 2.
Okay, so this is really interesting. So he's got this very different way of looking at these basic mathematical concepts.
Yeah, absolutely.
So where does he go from there?
So then he actually describes this experiment where he takes the conventional square root of 2, this 1.414, and he cubes it, and then he divides it.
Okay, so he's playing around with this number, seeing how it behaves.
Exactly. So what does he find when he does that?
Yeah, what happens when you cube it and then divide it?
Yeah, so he takes this approximation, he multiplies it by itself 3 times.
Right. Cubes it.
And then divides the result by 2.
Okay.
And what he finds is that this process yields a number that's around 2.828, which is the approximate value of the square root of 8.
Interesting.
And he finds this stable behavior under these operations to be kind of remarkable.
Because he's taking this number, this irrational number, and he's doing these repeated operations on it, and he's finding that it kind of stays stable.
It does. Yeah, it doesn't change erratically. It doesn't get really large or really small.
Okay.
And he actually calls the conventional square root of 2, he calls it, quote unquote, the number of steel.
The number of steel.
Because it doesn't really change. under these repeated operations.
So he's seeing this as kind of significant in some way.
He does, yeah. He sees it as further evidence that maybe there's something we're missing in our standard mathematical framework.
Interesting.
Because you would think an irrational number would behave a bit more, well, irrationally.
Yeah, you'd expect it to maybe go off the rails a little bit more.
Exactly.
Okay.
And then he brings in a couple of other concepts that are related to this. So he talks about the Fibonacci sequence.
Yeah, that famous sequence, 1, 1, 2, 3, 5, 8, and so on.
Yeah, exactly. And he sees this as reflecting a fundamental principle of growth in the universe.
Okay.
Where you start with 1 and 1, and then it doubles to 2.
Right.
And he views this doubling as this really important kind of concept.
Okay.
And he connects it to the concept of fractals as well.
Okay, so those self-similar patterns that you see in nature.
Yeah. And in those patterns, you often see doubling or related ratios. And so he argues that if the universe is, based on these principles of doubling and this recursive growth, then our math should really reflect that.
So he's saying that our kind of human-made mathematical systems should mirror those natural processes.
Exactly.
Okay.
And he thinks 1 times 1 equaling 1, and this irrational square root of 2.
Right.
They don't really do that.
They don't really fit that that framework of doubling and recursive growth.
Exactly.
Okay, so this is getting really interesting. We're kind of building up a different picture of mathematics here.
Yeah, it's definitely not the math that most of us learned in school.
Not the stuff from textbooks.
No.
Okay, so we've talked about his kind of issues with conventional multiplication and square roots, but he also talks about some broader implications of these ideas. He even mentions like Euclidean geometry and the Babylonians.
Yes, so he's very critical of Euclidean geometry,
Yeah.
The geometry that we're all kind of familiar with.
Right, with like lines and squares and circles.
Yeah, exactly.
Right.
And he sees it as this like historical inheritance from the ancient Babylonians,
Okay.
who he associates with confusion.
Confusion. All right,
Yeah.
so he's not a big fan of the Babylonians.
Not so much, no.
Okay.
He thinks that they didn't have it quite right.
So what's his issue with Euclidean geometry?
So Euclidean geometry is all based on the idea of a flat two-dimensional space.
Right.
And he says that's just not an accurate representation of our universe.
Which he sees as curved.
Curved and multidimensional.
Right.
And so he thinks that this reliance on this outdated geometrical system is kind of the root of many of our mathematical problems.
Okay, so he's going really big picture here, saying that, this whole system of geometry that we've inherited is kind of flawed from the get-go.
Yeah, he says it's a flawed foundation.
Okay.
And that it's led to all these misunderstandings about, irrational numbers, about multiplication.
Interesting. So if our current mathematical system is so messed up, what does he propose we do about it? Does he have like a better system?
He does. He calls it universal mathematics.
Universal mathematics. Okay. I like the sound of that.
Yeah.
So what's the basis of this universal mathematics?
So it's built on this foundation of a curved, multi-dimensional space-time.
Okay, so already a very different starting point than Euclidean geometry.
Right.
All right.
And he believes that the universe is constantly changing, expanding, contracting, and that there's this, kind of dynamism to it.
Okay.
And he also connects the number 1 to light.
The number 1 to light.
To light. And he says, quote, all things are light existing under different motion and pressure conditions, end quote.
All things are light. Okay, that's a pretty bold statement.
It is a gold standard.
So how does he back that up?
So he interprets E equals mc squared as supporting this idea.
Okay.
That all forms of energy and matter are really just different forms of light.
Okay.
And he sees everything as interconnected through these wave interactions.
So everything's kind of vibrating and interacting through these ways.
Exactly.
Okay.
And he even suggests that if you think about 1 times 1 in terms of wave interactions, it would result in 2.
Okay, because the waves would combine and create new patterns.
Right.
Okay, that's a very different way of thinking about multiplication.
Yeah, absolutely.
Okay, so we're getting this sense of a very interconnected, dynamic universe.
Absolutely.
And he also delves into particle physics, right? He talks about the standard model and some of the limitations there.
Yeah, so he critiques the standard model of particle physics.
Okay.
And he even notes that, even prominent physicists are starting to question this model a bit.
Mm-hmm.
And there's this emerging idea that, maybe reality is more about field
Fields rather than just particles.
than just
Yeah,
particles.
you're right.
Right. So he proposes his own alternative, which he calls the Terrarian wave fields.
The Terrarian wave fields.
Yeah.
Okay.
And he sees these as the fundamental building blocks of the universe.
Okay.
And he envisions them as these expanding spheres
Okay.
that are constantly undergoing action and reaction.
It's a very dynamic kind of picture he's painting.
Yeah, and he identifies electricity and magnetism as the two fundamental forces at play.
Okay.
And he sees electricity as being contractive and magnetism as being expansive.
Right.
And he even gives his own interpretation of gravity.
Okay, so he's really trying to rethink the fundamental forces of the universe.
Yeah, absolutely. And this all aligns with some other thinkers who've been critical of certain aspects of Einstein's theories, like Walter Russell.
Right, right.
So he's kind of in that camp.
Okay.
And then he introduces these kind of spiritual or symbolic concepts like the linchpin and the flower of life.
Okay, so we're going even beyond physics now.
Yeah. So he describes the linchpin or the quanta. He uses those terms interchangeably.
Okay.
As the smallest possible reflection of one.
Okay.
So it's kind of the basic building block in his universal mathematics.
Gotcha.
And then the flower of life, which is this geometric pattern of overlapping circles, he sees as this really important representation of the universe's interconnectedness.
Okay.
And he emphasizes that it's multidimensional,
Okay.
even though we often see it depicted in two dimensions.
Yeah, right, right.
And he connects it to all these ancient wisdom traditions.
Okay.
He talks about the Garden of Eden, the Tree of Life.
Okay, so he's seeing this symbol as a kind of bridge between, ancient knowledge and modern science.
Yeah, and he seems to think that this pattern holds like profound secrets about the universe.
Okay, so he's really weaving together a lot of different ideas here. Math, physics, spirituality, ancient wisdom.
Yeah, and he concludes with this really strong call to action.
Okay, so what does he want us to do with all of this?
He says we need to abandon what he calls, quote unquote, antiquated and dead works of the past in mathematics.
Okay.
And embrace this new understanding for the sake of creating a sustainable future.
So he's really challenging us to rethink our approach to math and to the universe as a whole.
Yeah.
Okay, so we've definitely gone on quite a journey here. We've explored Terrence DaShon Howard's very unique and unconventional ideas about math, about the universe. We've talked about his challenge to one equals one, his alternative understanding of the square root of 2, and then all of these broader implications that he draws from those ideas.
Yeah, it's a lot to take in, and it's definitely outside the mainstream of scientific and mathematical thinking.
Absolutely. I mean, he's really challenging some very fundamental concepts that underpin a lot of our modern world. Our technology, our understanding of physics.
Right. So it's hard to know what to make of all of this. I mean, do we throw out everything we thought we knew about math? I mean, I don't know.
Yeah, I don't think that's necessarily the takeaway here.
Right.
I think what's valuable is the spirit of inquiry, this willingness to question, to explore, to think outside the box. And that's something that our listeners, you folks in Deer Park, LaPorte, Pasadena, you embody that. You're always curious. You're always looking for new information, new perspectives.
Right.
And that's what makes this whole exercise so interesting is just seeing how someone can come at these really fundamental ideas from a completely different angle.
Absolutely.
And whether or not we agree with all of his conclusions, I think there's something to be said for that kind of intellectual adventurousness,
Yeah, I think that's a good point. It's not necessarily about agreeing or disagreeing, but it's about, being willing to consider different viewpoints, to challenge our own assumptions.
Exactly.
And who knows, maybe in the process we discover something new, we learn something new about ourselves, about the world.
Absolutely. And that kind of critical thinking, even when it's applied to seemingly abstract ideas like math, it can have a real impact on how we live our lives, how we engage with our community. It makes us more informed citizens, more effective problem solvers.
Yeah, and that's really what we're all about here, providing you with information and perspectives that empower you to make a difference right here, right now in your own community.
Absolutely. So on that note, we always like to leave our listeners with a question, something to kind of ponder.
Okay, I like it.
So thinking about Terrence DaShon Howard's ideas, even if you found them to be pretty out there, what other seemingly fundamental concepts, and not just in math, but in any area of knowledge, what other concepts might be worth re-examining? What other assumptions might we be making that we could question? Could a shift in our understanding of even the most basic building blocks of our knowledge, could that lead to new insights, new discoveries in other areas? It's definitely something to think about.
Yeah, I think that's a great question. And it's something that we can all apply to our own lives, our own communities. What are the assumptions that we're making that maybe we should question? What are the things that we take for granted that maybe we should take a second look at?
Exactly.
And by doing that, by questioning, by exploring, we might just find some really interesting and unexpected answers.
Absolutely. And if you found this exploration valuable, and you appreciate what we do here, bringing you these diverse perspectives, these thought-provoking ideas, you can support the show at thinkandactlocally.com/donate.
The link is in the show notes.
And until next time, keep thinking, keep questioning, and keep acting locally.